Hi, hello everyone. So in today's video we're going to have a little look at units of storage. So just like you have like units of measurements or units of mass or units of distance or whatever, your computers needs units for measuring digital information. Okay, so obviously you need to learn them all and their sizes. So let's start off with the very basics. Okay, so what do we know? We know that computers use ones and zeros to represent the flow of electricity. Okay, we talked about this before and we will talk about it in other videos again. Okay, so the one is obviously used to show that the voltage is over a certain amount, and the zero is used to show that the voltage is below a certain amount. This happens through the logic gates, and we've talked about that in the previous video. Okay, all the data we want in the computer is converted obviously into binary code, and in the next video we'll go through binary code, but that's what we're dealing with here. Okay, so, and this is very important, each one or zero is an individual bit. Okay, so a bit is a 1 or a 0. Okay, so what I've written down there is actually four bits. Okay, now let's try and put this into some type of kind of order. Okay, so a bit is a single 1 or a 0. It's a 1 or a 0. Simple as that. Okay, a nibble is 4 bits. So this whole thing, there are 4 bits, but that's also 1 nibble. Okay, a byte is 8 bits or 2 nibbles. Okay, and that's the basic unit. That's the unit we're most familiar with. Okay, that's the unit we're probably most familiar with. Okay, a kilobyte, small k, big B. Okay, a kilobyte is 1,000 bytes. So if it's 1,000 bytes, that means it's 8,000 bits. Okay, a megabyte. So megabyte is capital M, B, is 1,000 kilobytes. 1,000 kilobytes, so that means that a megabyte is 1 million bytes, which means it's 8 million bits. Okay, so where do we go from there? Well, we start going up in the bigger numbers. The next one, the one we're at the moment, gigabytes, it's 1,000 megabytes. The next one up to that, you can buy them at the moment, is terabytes, which is 1,000 gigabytes. And the next one after that, I've seen a few of them online, is petabyte, which is 1,000 terabytes. Okay, so that's the basic kind of unit organization that you're going to see. Now, let's delve into this a little bit. Okay, so you might sometimes see that unit to be defined as 1024 rather than 1,000. Okay, than the previous unit. The reason for that is it's powers of 8. Okay, but there's nothing wrong with doing this. Is right, for want of a better word. So byte is big enough to store. So just to put kind of things onto this, 1 byte can store about 1 character. That's about the kind of size you'd need to store an M or a Q or an X or a euro symbol. Okay, 1 byte. Okay, kilobytes tend to be used for songs, pictures, data. The same with megabytes. So that's where the range you are for songs, pictures, and documents. That's usually the range you're at if they're low quality. Okay, then kind of gigabyte, that's where you're storing video, apps, complex applications, and then you're kind of you're kind of into these three for storage, secondary storage. Okay, secondary storage. So that's where you are kind of at that one for the secondary storage. So that's the kind of the where we're at in terms of the storage end of it. Now, so each bit, if you think about it, can take either a 1 or a 0. Sorry, 1 or a 0. Okay, nothing wrong with there. This means that a nibble, if you think about it, a nibble is 4 bits, can have 2 to the power of 4 different values. Okay, and that means that a byte can have 2 to the power of 8 different values. Okay, so 2 to the power of 4 is 16 different values. 2 to the power of 8, 2 2 is 4, 4 is 8, 256 different possible values. Okay, so you can encode 256 characters onto in byte form, for want of a better word. And we've seen this, we will see this in a future video when we come to talk about ASCII. Okay, that there is a certain limit on the amount of bytes you can actually work with. Okay, so again, just to kind of get it into your head, so it is a possibility in terms of what you're kind of doing, with regards to your bits and your bytes. There's a lot to be worked with there. Okay, now I suppose that brings us on then to another idea. One of the cool little things you can do with a byte, and we'll talk about a byte, okay, is you can do what's called parity bits. Not parity, parity bits. Okay, so these are actually used to check errors. Okay, and they're digits that are added to the end of a number. So I'm going to show you what they are. So watch. Let's take a number. We were talking about binary numbers here now. So 1 0 1 0 0 1 0. Okay, so that's a number. Now you could work it out. That's 2 to the 1. What's that? 2 to the 0, 2 to the 1, 2, 3, 2 to the 4, 2 to the 6. So that's 2 plus 16, 2 plus 16 plus 2 to the power. So 82. Okay, so what's interesting about it is what they do in order to ensure that this gets transported through whatever computer system is there's only 3 ones in here. Okay, so what they do is they tag on a 1 at the end. Okay, so when the computer reads it, it reads this one, and if it sees that it's a 1, then there should be an odd number of 1s there. Okay, it won't know how many there is, but there should be an odd number. So it's a way of checking to make sure the right number of 1s have come through. Okay, and similarly, let's take one. Okay, let's take this one here. It has 4, so it is an even number. Okay, so what it does is puts a 0. And then when the computer is reading, it reads the 0 first, reads the 0 and says, okay, it should have an even number of 1s. Yeah, I do. So if this happened, and this is where it gets really cool. I just make one up for the sake of it. 1, 2, 3, 4, 5, 6, 7, and there's 1, 2, 3, 4, 5. If this happens, well then, the computer reads the 0, and it says, okay, that should be even. Something's wrong. Okay, go back and check, or error signal or whatever. Okay, and similarly, you know, if you have something like, you know, give you another example here. Let's say I have 3 sets of code. Okay, so these are all 7 digits, and you know we are talking about 7-digit codes, not 8 digits. Even though we know we can write to 8, we're dealing with 7 because most of them are done till 7 in fairness. So there's been an extra one added on to the end, but one of these is wrong. Sorry. So code A, code B, or code C. One of them is wrong. In other words, we've added a parity bit to the end of each of them, but one of them is wrong. Which one is going to spit out the error? Okay, give you 3, 2, 1, see can you figure it out. 3, 2, 1. And we're back. Okay, so we'll do our checklist. Okay, there's a 1 and an end. Okay, so a 1 and an end tells me I should have an odd number of ones. Uh-oh, that's wrong. It has an even number of ones in the 7-bit code. Let's try this one. There's a 1 at the end. I should have an odd number of ones. Yeah. There's a 1 at the end. I should have an odd number of ones. So A was the wrong one. Okay. So you see how handy it is. Okay. Now obviously this doesn't work for an 8-bit. So it doesn't work for a 1 byte because you'd be adding 1 extra code in to make it 9, and we know that there's trouble with that. We'll see that in a while. But for 8 or 7 or 6 or 5, it works perfectly. Okay, you're just tagging in an extra 1. Okay, what you're doing is in the code that you're doing, you're reading into the code to ignore to treat this one different than the calculation for this number. So rather than, if I was to give you a 7-digit code, I'll take this one. 101011. Okay, so if I was to give you a 7-digit code, you'd go 2 to the 0, 2 to the 1, 2 to the 3, 2 to the 5, 2 to the 7. So if I give them to you like that, you'd probably go, that's 1 plus 2 plus 8 plus 2 to the power of 5 plus 2 to the power of 7. You go 171. But the computer knows that in this particular scenario, this just indicates a parity bit. So it's just checking. So when you see that, it'll say, okay, odd. Check that it's odd. It's not odd. But the reality is what you're trying to get it to do is you're ignoring that. The computer, if this was true, the computer would just go 2 to the power of 0, 2 to the power of 2, you get the idea. 2 to the power of 4, 2 to the power of 6 would be a totally different number. Okay, so it ignores the first one because it's the code that it's encoded with in the ACLU knows to ignore the first one. Okay, now do all programs do that? No, there's other methods around this. It's not a kind of a hard and fast system, but it is a handy little system of doing it. So it is pretty cool, has to be said. Okay. I'm trying to think now, is there anything else there that might? Yeah, that's all I can think of right with them, really. You know, it's a pretty complicated area, but it's good for you to know if at a very basic level that you can build in little checklists that would allow you to do that. Okay, so I suppose the moral of this story is you know your bits, know your nibbles, know your bytes. Okay, it's as simple as that. Okay, 1 bit has only 2 possible outcomes. 1 nibble has 16 possible combinations of 1s and 0s. A byte has 256. Okay, you can imagine how many is in a kilobyte. You know, that's the reality of it. Okay, so that's it. Okay, thank you very much.